Imagine two people who have never met could do an amazing trick. Alice and Bob are allowed to communicate over a line which is tapped, so any message they pass will be intercepted by Eve, who is always listening. The trick is to agree on a secret numerical key, without Eve also obtaining a copy. How is this possible? First, let's explore how this trick is done using colors. So how could Alice and Bob agree on a secret color without Eve finding it out? The trick is based on two facts. One, it's easy to mix two colors together to make a third color. And two, given a mixed color, it's hard to reverse it in order to find the exact original colors. This is the basis for a lock, easy in one direction, hard in the reverse direction. This is known as a one-way function. Now, the solution works as follows. First, they publicly agree on a starting color, say yellow. Next, Alice and Bob both randomly select private colors and mix them into the public yellow in order to disguise their private color. Now, Alice keeps her private color and sends her mixture to Bob, and Bob keeps his private color and sends his mixture to Alice. Now the heart of the trick. Alice and Bob add their private colors to the other person's mixture and arrive at a shared secret color. Notice how Eve is unable to determine this color since she needs one of the private colors to do so. And that is the trick. Now, to do this with numbers, we need a numerical procedure which is easy in one direction and hard in the reverse direction. This brings us to modular arithmetic, which is known as clock arithmetic. For example, to find 42 mod 12, we take a rope of length 46 units and wrap it around a clock of 12 units, which is called the modulus, and wherever the rope ends is the solution. So we say 42 mod 12 is congruent to 10. Easy. Now, to make this work, we need a prime modulus such as 17 instead of 12. Then we find the primitive root of 17, which is a number that has no factors in common, in this case 3. And it has this important property that when raised to different exponents, the solution distributes uniformly around the clock. 3 is known as the generator. So if we raise 3 to any exponent x, the solution is equally likely to be any integer between 0 and 17. Now, the reverse procedure is hard. Say, given 12, find the exponent 3 needs to be raised to. This is called the discrete logarithm problem. And now we have our one-way function. Easy to perform, but hard to reverse. Given 12, you would have to resort to trial and error in order to find the matching exponent. How hard is this? Well, with small numbers, it's easy. But if we use a prime modulus which is hundreds of digits long, it starts to get seriously hard. Even if you had access to all the computational power on Earth, it could take thousands of years or more to find the answer. So the strength of a one-way function is based on the time needed to reverse it. Now this is our solution. First, Alice and Bob publicly agree on a prime modulus and a generator, for example 17 and 3. Then Alice selects a private random number, say 54, and calculates 3 to the power 54 mod 17 and sends this result publicly to Bob. Then Bob selects his private random number, say 24, and calculates 3 to the power 24 mod 17 and sends this result publicly to Alice. And now the heart of the trick. Alice takes Bob's public result and raises it to the power of her private number, which gives 3 to the power 24 times 54, and she obtains the shared secret, which in this case is 1. Bob takes Alice's public result and raises it to the power of his private number, which gives 3 to the power 54 times 24, resulting in the same shared secret. Notice they did the same calculation with the exponents in a different order. 24 times 54 is the same as 54 times 24. Without one of the private numbers, Eve will not be able to find the solution. And this is how it's done. While Eve is stuck grinding away at the discrete logarithm problem, and with large enough numbers, this will literally take forever.